Eric, Car Guy here. Today we are going to cover the basics, the basic parts of an engine. I get a lot of requests on engines and how they're put together and what the little parts are on the inside and what they do. I plan to cover that today. I'm not necessarily going to get into a lot of theory, but I have this Integra engine, which you may recognize from the oil pressure video, that is just kind of sitting here, and I'm just kind of sitting here. So rather than sitting here, I thought, man, why don't I think about those people that watch my videos and give them something that they asked for? So let's give you something you asked for. We're just going to point and name the parts. How's that? First, we'll start with this. This is a motor. It's a starter motor. This is a 1.8 liter Honda engine. It was in a 1990 Acura Integra. It is not a motor. It is an engine. Of course, if you use the word motor, yeah, people are going to know what you're talking about, but technically you would be wrong. Engine is actually short for ingenious device. Motor is actually something that represents an electrical component. So this is not technically a motor. This is an engine. This is the valve cover. Under the valve cover, we have the camshafts. This is a dual overhead cam engine. Not every engine is designed this way. There are lots and lots of different engine designs. Everything from these traditional four-stroke types to, let's say, the rotary types that you might find in a Mazda. Those are fun. That engine started out as a water pump. With this dual overhead cam system, you have two camshafts, each controlling a different function. This one is the exhaust camshaft, and this controls all of the exhaust valves. This is the intake camshaft, and it controls all of the intake valves. We know this is the intake because the intake manifold is on this side and we can see the flow of air into the engine. We know this is the exhaust side because these are the exhaust valves and leads out to the exhaust manifold of the engine. This is a camshaft, or sometimes referred to as a bump stick. Why? Bumps. These are the cam lobes. Now this really is everything, because this says how this engine is going to breathe. This tells it when to open the valves, how long to keep the valves open for, and how far to open them. That is huge, because that is, like I said, directly proportional to how the engine breathes. So if you want to change an engine's behavior, you want more horsepower, less horsepower, you want more torque, you want more fuel economy, all these things come down to this guy right here. And they all have to happen at a given time. Hence the reason we have timing gears on them, so that everything works together.
While editing this, I believe I came up with an even better analogy for a camshaft. Think of the camshaft as a computer program, a mechanical computer program for the engine. So whenever you're thinking of camshafts, think of them as mechanical computer programs because they dictate the behavior of the engine and how it breathes.
These cam lobes, as they spin around, push onto these followers on this particular engine, and in turn they open the valves. This engine uses these followers. So the camshaft pushes on this, which takes its leverage from here and then pushes down. This is actually the valve. This is an exhaust valve. So what this little thing does is it sits down inside of here, and every time the camshaft comes around, it pushes down on these, thus opening the exhaust valves. You have them all the way across for each one of the exhaust valves. And this engine has 2 valves per cylinder on the exhaust side and 2 valves per cylinder on the intake side. It's a 4-cylinder, so 4 times 4 is 16. So it's a 16 valve dual overhead cam engine. Once again, lots of different engine designs. In a pushrod engine you have lifters. So you'll have either solid or hydraulic lifters. Hydraulic lifters means that this guy's filled with oil, and that this little thing in the middle here will squish down a little bit. And these allow for quieter operation of the engine, but with a solid valve train, you actually have more accurate valve timing, because this is like a squishy sponge. A solid valve train is exactly that. It's going to open the valve precisely. These are not so precise, but mostly used in passenger cars to keep, you know, the services down. because with solid valves you have to adjust them periodically. With hydraulic lifters you do not. This is a push rod, and the push rod sits inside of that little cup there on the lifter, and every time the cam comes around, I realize this is not the cam for this car, but every time the cam comes around, what it does is it pushes up on that lifter and opens the valve. It does it in kind of a roundabout way. That's why overhead cam engines came about. This is the intake camshaft, and this is the exhaust. And if you look at the bumps, they're a little different. One's a little higher than the other, maybe a little fatter. But the point is these things are angled and put in just the right position so that they can activate the valves. And we want to do this once again so that we make the engine breathe. Back of the intake camshaft has that little slot that just drives the distributor. So the distributor is mechanically connected to the camshaft, so if the camshaft is out of time, the distributor is too. Keep that in mind if you're doing timing belts and things aren't running right afterwards. This is an old school distributor, and this no rotor here. But what this does is this is mechanically connected to the camshaft and driven by the camshaft. And what it does is it transfers the spark to each one of the cylinders as the cylinder comes up on its compression stroke. So this is mechanically timed to the engine via that gear, which is in many cases splined to the camshaft. This is not the correct camshaft, but this is what turns it. So if you take one of these out, you have to make sure you put it back in the right place or your engine's not going to run right. This is an old school oil pump. It bolts to the block, and there's that little area right in here that is driven by a long shaft that actually many times is run off the distributor. So the distributor and the oil pump are often sort of tied together by this rod that connects the two. So the camshaft also drives the oil pump. Something to keep in mind. So if your camshaft isn't running and you don't have oil pressure, you may have a problem with the connection between these two. Here we have the exhaust manifold. This is the dipstick for the oil. Goes down into the oil pan. Each one of these is a runner that comes out of each cylinder. So each cylinder has its own runner. They all collect inside of the manifold. Things that collect things are called manifolds. You have the intake manifold in the back, and then you have the exhaust manifold here. These runners are all the same length. Reason for this is as the engine runs, it sends out pulses on each cylinder individually at different times. And each pulse actually helps draw out the next pulse from the next cylinder. So they all need to be the same length so that each cylinder can produce equal power. You hear the term equal length headers. It's kind of what they're talking about. It's something that you need in the design of the engine. If not, it won't run smoothly. So you want all these pieces of metal, no matter how you bend them, to be roughly the same length when they reach the point where they all come together. There's your exhaust manifold. Like I say, all four of those holes collect down into that one big hole. Exhaust manifold. In case you were wondering, if you take that plug out, it empties out the coolant inside the block. I feel like I should have talked about this first, but the camshafts sit up here and keep the top part of the engine in time. The crankshaft is down here, and this keeps the bottom half of the engine in time. And these things are normally connected by a timing belt, and the water pump lives here, which is driven by the timing belt. So, and this is the tensioner. It keeps tension on the belt, but there's a belt that connects the crankshaft with the camshafts. It's called the timing belt because that's what it does. It keeps the engine in time. It keeps the valves opening and closing in time with the pistons moving up and down, which is the crankshaft, which we're about to get to. The water pump, of course, moves water throughout the engine. Other engines, this is an older V8 setup, use a timing chain. And this upper big gear here would be connected to the camshaft, and the lower one here would be connected to the crankshaft. And the reason this gear is bigger, for every one revolution of the camshaft, you have 2 revolutions of the crankshaft. And the reason for this is it's a 4-stroke engine cycle. So it's designed in such a way to where every time the camshaft goes around once, the crankshaft has gone around twice. Kind of cool, huh?
You may also hear the term double roller timing chain, which refers to this, which is 2 chains put together, which is really stronger. In addition to that, you might hear of gear-driven setups, which are more accurate but also noisy. You can put these in place of regular chains, and some engines are just gear-driven from the start. I've seen a lot of diesels this way.
This is the intake manifold. Just like the exhaust manifold, it has different runners going into each one of the cylinders that are all the same length. Air comes in here, goes down through these runners. Each one of these goes down through each one of these runners into each corresponding cylinder. Intake manifolds. I'm not going to get into the principles right now, but intake manifolds that have long, narrow runners are usually good for torque. Well, are made for low-end torque. Whereas, like say, short runners that are big and fat, that is made for high RPM horsepower. What happens with these long, narrow runners is they help increase the velocity of the air going into the cylinder, and on a naturally aspirated engine, it helps increase torque. Conversely, when these are big open areas, they allow the engine to draw in more air at a higher RPM, which in turn gives it more power. These, across here, are all of your fuel injectors. But anyway, these little fuel injectors sit underneath what is called the fuel rail, which supplies pressurized fuel behind the injectors themselves. Then what happens is each one of these injectors will spray into the individual cylinders at the correct time. According to the computer, it uses all the different sensors on there, such as cam and crank sensors, to know exactly where the piston is, to know that the intake valve is open. And each one of these provides a little squirt. So in this case, in the case of a fuel injected engine, you have air all the way to this point. Then fuel is added at the last second while the intake valve is open. In a carbureted engine, there's air and fuel in each one of these individual runners going down into here. This orange stuff here is all gasket. So that's the intake gasket. It seals, well, what would be EGR here, and coolant goes through here. But check it out. There's the valves. These are the intake valves, and they're both closed right now because there's no camshaft in there. One on that side, one on that side. Notice how this area in here is all clean. That's where the gasoline gets sprayed. So the air goes in. Every place else is kind of carboned up. The shape of this is very important because the air moves like liquid. So you want it to flow in here. And as these valves open up into the cylinder, they allow that air and fuel to pass into it. And what you're looking at here at the top is actually the valve guide, and that's the valve itself. Let's see if we can pop one of those out in a minute. And here is the exhaust side, which has kind of the same thing. But instead of stuff coming in, stuff's coming out. So this is the beginning of your exhaust system. That brown crusty stuff, that's burned oil. This is the cylinder head. Between the cylinder head and the block, you have the head gasket. These are dowels that guide where the head gasket goes. But this head gasket's just fine. There's nothing wrong with it. What you'll see here is the combustion chamber, or at least part of it. These come in all different shapes and sizes. Some of you out there may be familiar with the term Hemi, which actually stands for hemispherical. This is, what do they call this? A pented roof? Penta roof design. But the hemisphere design is like the inside of a sphere in here. So this is spherical inside the combustion chamber. That's where that term hemi comes from. It's hemispherical. This, I believe, is called a pentaroof design because it goes up and comes down at a sharp angle, as you can see on each one of these. The design of this, the angle of these valves, all of these things weigh into how the engine performs. Every little nuance, every little measurement, right down to the thousandths of a millimeter, all of this comes into play with an engine. So engineers spend a great deal of time designing the shape of this, designing how big these valves are going to be, everything else, all to come together so that the engine works within a certain range, certain parameters. And in the case of an automotive engine, they're trying to balance between fuel economy and power. It's that simple. It's not an easy thing to do, but the people that are good at it, good for them. This is the top of the valve. This is the valve spring, and these are the keepers. There's two of them that hold in the valve. Here is your valve spring. Here's the retainer. And these are the keepers. But these actually sit down inside of this groove, and they're tapered, as you can see. They have a taper to them. Fatter at the top than they are at the bottom. And they sit down inside here and grab onto the top of the valve. So they sit in there, and because this hole is tapered, they're wedged in, and they just wedge together. And on the inside of these keepers, there's a groove that you see there, and that groove sits in the top of the valve right here. So that holds it all together. Seems kind of cheesy, but it stays together for the most part. But what I just removed here is an exhaust valve, and as you can see, it's kind of crusty. Got a little bit of oil on it, so that valve seal may have been leaking a little bit, but it's probably more likely that the rings on this engine are worn out because it's got quite a few miles on it. Now the shiny spot is called the seat, or the shiny spot of the valve is where the valve contacts the valve seat, which is here, the cylinder head. So this area here needs to seal against this area of the valve. Whenever a valve job is done, this seat is cleaned up, sometimes at many different angles. Sometimes they grind the seat up to 5 different angles, 5 different sides of stones. But they have a special tool that fits down in to this valve guide and grinds this hole in such a way to where it will seat up against this valve. Sealing is very important in an engine, especially in the combustion chamber. Any leaks cause compression loss, and any compression loss causes power loss. But that's the basics of how a valve stays inside of a head, held in there by keepers. Now, valve springs are also very important because after the camshaft compresses them and opens the valve, it's the job of the valve spring to close the valve again. And it's equally important that the valve closes as efficiently as it opens. So valve springs are important in that they need to be able to combat the forces that are going against them, and they need to rapidly re-expand to close the valve. If not, it's something called valve float, to where the spring, or the speed of the valve, overcomes the ability for the spring to close the valve. In fact, right here is probably the #1 limiting factor of RPM. High RPM engines have really good valve springs that are able to close the valves once they're open. But you got to think, if something is moving at 10,000 revolutions per minute, which is really super fast, if this spring has to compress and decompress in that amount of time, which is milliseconds, it's not able to keep up. The stronger these are, the more stress it's going to put on the cam and the whole valve train. But if they're too weak, then what happens is they won't be able to close the valves, and the valves will stay open. And if the valve stays open, then you lose compression and you lose power, and it starts to miss and have issues there. Now in this engine, this is the valve seal. And these are positive type valve seals, meaning that they slip over the top of the valve guide itself. And the valve guide is basically a metal sleeve that this is sitting on top of, that the valve rides in and out of. Okay, here's one of those valve seals. And this is referred to as a positive type valve seal. And the reason is because it positively locks onto the top of the valve guide. If you have bad valve seals, a lot of times it will suck the oil, well, on the intake side mostly, it will suck the oil from inside the cylinder head down inside the combustion chamber, and this is not a good thing. These positive type valve seals, however, are very good at keeping the oil out. Some valve seals are just what are called umbrella seals, and they just sit on the inside of the valve and don't make a positive seal here at the valve stem. They really look like an umbrella to help keep this out. If the valve guide gets worn out and the space between the valve guide and the valve gets too big, it will suck more oil in there, which will cause you to burn more oil. But I'm of the opinion that most of the oil consumption actually happens in the bottom of the engine, because that's where most of the pressure is. Let's go there next. Alright, now let's get a look at the crankshaft. Oh, by the way, as long as we're at it, this is a flywheel. This is a manual transmission. So when you have a manual transmission, this is a weighted thing, it's called a flywheel. If this were an automatic transmission, this is a thin plate, and it's referred to as a flex plate, not a flywheel. Flywheels are on manual transmissions, flex plates are on automatics. This is a flex plate. As you can see, it's much thinner and lighter, but these are for automatic transmissions. The thick ones that are heavy are flywheels. This is referred to as a flex plate. So what does it look like as your engine runs? All I'm doing is turning the flywheel. So, four-cylinder engine fires every 180 degrees, so as both of these are up, watch the four-stroke engine cycle to see more stuff on this. But as both of these pistons are up, one of them is on the compression stroke and about to fire and go on the power stroke, and the other is on the exhaust stroke. There's something called sister cylinders, and it has to do with the crankshaft design and the way this whole system is set up. That's what that means. That's why two of these are always coming up at the same time. Same with these middle two. Sister cylinders. Cool, huh? Alright, now let's flip this guy over. You know, I'm going to be dumping oil all over the place. I'm not too worried. Let's take the oil pan off. This is the oil pickup. So as the engine runs, oil gets sucked up into here by the oil pump, which is this assembly on the front of the crankshaft and is driven by the crankshaft. This metal plate is referred to as a windage tray. So, and some of these are actually designed to actually scrape a small amount of oil off of the crankshaft as it rotates to help it be more efficient. Oil pickup. Got a little screen down in there, so it'll help keep out any big chunks from getting sucked up in there. But it goes to the oil filter also. That's the reason why you have it on there. So if there's any dirt or anything in here, it should get caught up by the oil filter or this screen. It could be said that this is where the rubber meets the road, because in essence what an internal combustion engine does is it turns the chemical energy inside of the gasoline into mechanical energy, and that happens right here at the crankshaft. These are counterweights. These are connecting rods. These are directly connected to the pistons. In fact, we're going to take one of those pistons out of here now. But as it rotates, and with a four-cylinder engine, it's hard to keep it balanced. So what they often do is they have these harmonic balancers. There's a little piece of rubber that is in between the inside and outside of this pulley. And the reason for that is because every time a piston pushes down and causes this to rotate, it creates a pulse. But that pulse pretty much ends when it gets to the end of its travel, and then it has to compress something. So it goes from accelerating to decelerating, accelerating to decelerating. And this creates pulses of power here at the flywheel and the crankshaft to help even that out so that it doesn't shatter itself, because believe it or not, those pulses are not good for the metal parts inside the engine. This is called a harmonic balancer, or a damper, because that's exactly what it does. Is this helps dampen those accelerating and decelerating forces that happen at the crankshaft. This guy right here is actually more important than you might think. So this is what it looks like rotating from below. You got these, the connecting rods that are connecting to the pistons coming up, and they're all transferring power to their respective journals and transferring it here to the back of the engine. So when they say power at the flywheel, like 140 horses at the flywheel, this is what they mean. That this has enough twisting force. Horsepower is actually derived from torque, and torque is a twisting force. So really, torque tells you more about an engine than anything else. But more torque equates to more twisting force, more of the engine's ability to push down. Bigger cylinders and other factors contribute to an engine that can have more torque, camshaft design being one of them. I'm not going to take the crankshaft out, and I'm sorry to say, but I will. This is your last thing. I am going to take one of the connecting rods out. And here is the bearing cap. You might remember this from the oil pressure video. And that bearing is not looking so great, but see, the bearings have these little tabs on them, and they fit down into these little slots here on the caps. So you just slide them down into place like this. See how they fit in there all nice? This journal right here has to be completely round. It's really important. It also has to be nice and shiny and smooth, because this is where the power is transferred. You want it to happen smoothly. Okay. See a piston being born? Alright. Ta-da. We have in our hands a piston. This is the hole that was left by the cylinder. Now this normally should have a crosshatch pattern on the inside of it, because that helps the rings seal and the oil control rings work. But there is the crankshaft journal. And think of the crankshaft like pedals on a bicycle, and each one of the pistons are like legs pedaling the crankshaft. So it works in a very similar way. Here is piston. It's fairly light. Actually, this one's still nice and stiff. But that's it. 4 of these that make up the displacement. So when you hear 1.8 liter, like in the case of this engine, that means the volume between all 4 of these cylinders and pistons comes out to be 1.8 liters of displacement. That's how much air this displaces. Shiny spot right here is called the skirt. 3 little grooves up here. The first one with a little wavy plate in it, that is the oil control ring. Then you have 2 compression rings. You have this compression ring and this compression ring. So an engine, or a piston, normally has these 2 compression rings and an oil control ring. So when people say they're re-ringing the engine or putting new rings in, that's what they're talking about, is those piston rings, because these guys are the things that seal against the inside of the cylinder. This right here is the wrist pin, and this allows the connecting rod, which is this part, to pivot. Power is transferred as this piston comes down. You see it has to change direction as it moves up and down on the crankshaft. The little dents in the top are for the valves when they come down. So sometimes the valve is really that close when it opens up, and the piston is all the way up. So that's what those little grooves are for. So the piston's all the way up, those little valves come in like that. And that is pretty much your engine. And then there's these little holes once again, remember the whole oil pressure thing? That is actually forced out this other little hole, which lubricates the bottom of this area in here. So this will squirt up and throw oil up under the bottom of the piston, which helps, one, keep it cool, because you got to think it's really hot on this side of the piston. In the combustion chamber, it's like over 2,000 degrees in some cases. But they're getting rid of that heat with the cooling system. That's why the cooling system is so important. An engine turns the chemical energy from your gasoline into mechanical energy here at the piston and the crankshaft. That's what it does. You want to know the really scary part? It's only 20% efficient. 80% of the heat that's generated by the chemical energy of the gasoline is lost through friction and other things. Other loss of motion. It's not very efficient to take a piston and move it up and down 3 times in order to get one thing of power out of it. It's really not that efficient. But the internal combustion engine is not really that great. We've got it to a point where it's about as good as I think it's going to be, because we've got combustion down to a science. But still, you can't fight physics. At the end of the day, this is an extremely inefficient way to make power. It works, it's common, it's cheap. Efficient? No, not so much. I'm going to cover more specifics of this stuff at some point in time. But this, once again, just a general video. Just a video to say, these are the parts inside the engine, this is what they do. If I missed something, or if you have something to add, feel free to add it in the comments. But come on, be nice. Some of you out there are kind of uptight. I'm here to learn just like you, and I am learning just like you. But this is what I know of the internal components of the engine and how they work. And I hope this information was helpful to you. You can always visit me at ericthecarguy.com.